Welcome back to what I think is going to be the last video for the Calculus 1 playlist, and in this video the motivation is going to be to look at indefinite integrals, and in the last video we looked at definite integrals, and we found out that we had a few brilliant fellows that discovered something game-changing for calculus, and that's if we had some definite integral from a to b of some function of x with respect to x. We could say that that's equal to some function capital F of x evaluated at b and a, which is also given right here. And we call that capital F the antiderivative of that lowercase f. And we looked at an example where we had the definite integral from a to b of x with respect to x, or dx you'll also hear. And we found that that was equal to 1/2 x squared, again evaluated at b and a. And what we could say is that 1/2 x squared is the antiderivative of f of x, which was just equal to x. And one little cliffhanger that we didn't really talk about, but we're going to talk about in this video is, what about considering a different antiderivative function, and let's say it's equal to 1/2 x squared plus c, where this c is just some constant. And if we take the derivative with respect to x of capital F2, well, that is simply going to be equal to 1/2 times 2x plus the derivative of that constant with respect to x. And we know the derivative of that constant is going to go to 0. So if we took the derivative of this capital F1 function, we got x. And if we took the derivative of this capital F2 function, we also got x. So which one is the preferred route to go? And is there a difference between the two? And we could actually kind of do something that looks a little bit funky. You probably won't see it in textbooks. But we could say that if we have some definite integral, that's actually equal to this kind of standard or generic antiderivative. So we would have some capital F function and then plus some constant. And both of these terms would be evaluated at b and a. And if we do this evaluation, if we consider b first, so you would have f of b plus that constant, that quantity minus when we evaluate at a, so f of a plus c. And when we subtract these terms, you will see that the c's cancel out and we're simply left with f of b minus f of a. So again, we are left with our original result that we established up here. And we could actually use this f2 function all the time, but it's a little bit redundant because we know that these constants c are going to cancel out. But now we can get into the purpose of this video where we look at indefinite integrals, and we actually need to include that plus c. Because the way that we structure an indefinite integral, we get rid of those limits of integration. And this plus c is very important when you have this indefinite integration. And all the time, if not all the time, at university, your professor or lecturer, they will definitely mark points off if you miss this plus c on an indefinite integral. And one thing we can take from the last video is that trial and error sucks for trying to find these antiderivative functions. But if you haven't seen that video, please check it out. It should be a pretty long video that a lot of work went into. Appreciate it if you like or comment that video. Or if you like and comment on this video, or even share it, or even subscribe. Everything helps. Because if you did any of those, then we have unlocked the antiderivative table, or what we can call the indefinite integral cheat sheet. So there's 8 integrals listed here. So if we have that integral, x raised to the minus 1 dx, we can say that that's equal to the integral of 1 divided by x dx. And now we actually have to refer back to the previous video where we looked at what the derivative of the natural log of x was. But to get there, we actually had to look at what the derivative of e to the x was, which was a very interesting procedure to go through. And what we recovered from that derivative, using a trick, we found that the derivative of the natural log of x with respect to x is equal to 1 divided by x. So now if we take that result and kind of go backwards, the integral of 1 divided by x dx is equal to the natural log of x. But again, don't forget that plus c, because if we take the derivative with respect to x of the ln of x plus c, we know that that is going to be equal to 1 over x. So that's where this condition that n cannot equal 1, that's where that comes from. And now we enter into something, a significant amount of importance is actually on this, And it is going to be what we call the fundamental theorem of calculus. Now in this fundamental theorem, there's a part 1 and a part 2. And in the last video, or the start of this video, we actually had one of the parts in there. So now we're going to look at the second part. And we're going to consider an interesting looking integral. So we're going to have the integral, except it is a definite integral. So we have the integration limits from a to x of some function f of t with respect to t. And we're going to say that that's equal to g of x. And we're going to keep some rules here. So we're going to say that f is continuous on some interval of a to b. So if we plot out what we're looking at right here on the right, so we have some function y, we have some interval a to b, and we just have some value x that is in between a and b. And what this integral is saying right here, I guess you could think of it as the area to date, or the area so far. So at this x, we're considering this area. Once x moves a little bit, now we're considering that additional area. And in university, I found it useful to kind of evaluate this integral from what we know. So we could also say that this is equal to some capital F function evaluated at x minus that capital F function evaluated at a. But we're going to go another route, and we're going to look at what the derivative of g of x is. So we can plug in our standard definition for the derivative of g of x. So we have g of x plus h minus g of x divided by h, and we're going to set that limit as h goes to 0. And we're simply going to plug in for g of x plus h and g of x this integral right here. So we can also represent that by these terms that are in this right hand side. So notice here we're changing that limit x plus h, and then we have x. But from the property of integrals, we know that we can break that integral from a to x plus h into two separate integrals. So we have a to x and then x to x plus h. And if we plug this result in right here, well, then we get that this term and this term will cancel out, and we're simply left with just this term right here. So our integration limits are x to x plus h, and we're going to set this equal to what we found right here, just that standard definition of the derivative of g. And recall how we can represent g. So we can have f of x minus f of a. So if we look at g of x plus h, that's going to be equal to f of x plus h minus f of a. If we take the difference of those two, we simply get f of x plus h minus f of x. And now we can start to compare this whole term right here. So if we look at the left-hand side, we could represent this entire integral as a function that looks like this. Don't forget to carry through the limits as h goes to 0, and then we have this 1 divided by h term. And if we actually consider this term as a whole, what you can see is that this is, by definition, the derivative with respect to x of that capital F function, which is just going to refer us back to that lowercase f of x function. And now if we consider the right-hand side where we had that definition of the derivative of g with respect to x, from what we found above, we know that that is going to equal the limit as h goes to 0, 1 divided by h, and then the quantity of f of x plus h minus f of x. So here's our term here. And notice with both the left and the right hand terms that we have matching terms here. So we can actually represent this in a different kind of way. We could consider this term here and this term here, and we could say that g prime of x, or the derivative of g with respect to x, is equal to f of x. Or you might also see that represented as the derivative with respect to x, where we had g of x, we plug in that original integral, so a to x, then we had f of t, and then dt, and that is going to be equal to f of x. But for now, we can reflect on what we did in this course. I think we had 10 videos where we looked at limits, derivatives, a little bit of integration, and I think this hits on all key points for a Calculus 1 course. In the beginning of the course, I said I wanted to try to get through this pretty quickly, just to build a background of knowledge for the courses to come in electrical engineering, so we needed to have Calculus 1, 2, 3, and differential equations to really move forward. And I think most of the important concept we've covered, especially geared towards someone that's in engineering or is going to be pursuing engineering. So I think we can actually move on to the next course, which is going to be Calculus 2. Makes sense. And if you learned anything new or useful in any of these videos in this entire course, please like, comment, share, subscribe. As always, helps the YouTube algorithm. Thank you for watching, and we will see you in the next series.